Hello, and welcome to the Terraform Learning Series. I'm so glad you're here joining us for this explainer. Today, we're going to gently peel back the hood of Terraform to really understand the internal engine that powers the whole thing. If you're looking to build a rock-solid foundation in infrastructure as code, well, setting a calm, methodical pace to demystify these concepts is exactly where we need to begin. Have you ever found yourself wondering how this is even possible? I mean, how can a single tool communicate with hundreds of wildly different platforms, from AWS to Azure to your local Docker containers, literally all at the same time? Well, the secret lies in its split internal engine. It's a beautifully separated architecture, and it's what makes the whole system so powerful. Okay, let's dive into this. Here is our roadmap for today. We're going to start with the magic of Terraform, break down the brain, which is Terraform Core, and then the translators, the Terraform providers. After that, we'll connect the brain and the hands, look at some essential DevSecOps best practices, and wrap up with a quick summary and your next steps. Let's start with Section 1, the magic of Terraform. You know, in modern high-tech environments, manual infrastructure management is honestly a bit of a nightmare. Clicking through endless web portals or relying on duct-tape scripts, that's basically an open invitation for human error. It really is as slow as maintaining a massive library system without a written index. Infrastructure as code, or IAC, completely replaces those manual clicks with standardized code. It introduces this profound speed and repeatability to your day-to-day work. And this magic comes to life through a really elegant four-step lifecycle. First, you just write your infrastructure code using HashiCorp Configuration Language, or HCL. Next, you run your init command to initialize the environment and pull down the necessary plugins. Then you generate a plan. And this is great because it lets you preview exactly what's going to be created, updated, or deleted before you commit. Finally, you hit apply, which executes the changes and actually provisions your infrastructure in reality. Moving right along to Section 2, the brain, Terraform Core. And this brilliantly illustrates how the system is actually split up. Think of Terraform Core as a video game console, or maybe your smartphone's operating system. By itself, a console doesn't actually play a specific game, right? And your phone's OS doesn't have a specific app built in. They just provide an incredibly smart underlying engine. To actually do something, like, say, provision an AWS server, you have to plug in a game cartridge. In the Terraform world, those cartridges are your providers. So acting as that central brain, Terraform Core is actually written in Go, which gives it top-tier performance. It parses your configuration files, manages your JSON state file, which, by the way, is the absolute record of your current reality, and it generates your execution plan by constantly comparing what you want against what already exists. To make those comparisons safely, the core relies on a dependency graph. Let's say you define a virtual machine that needs a specific network to function. Well, Core uses graph theory to mathematically map out that the network absolutely must be built first. And to keep things incredibly fast, it can actually process up to 10 of these operations concurrently by default. It's just a highly methodical, efficient way to build out complex environments. Now for Section 3, the translators, also known as Terraform providers. Now, what's really interesting about this slide is the strict separation we can see going on here. Terraform Core remains completely isolated from the cloud platform itself. It only ever talks to the plugins, the providers, sitting in the middle. It's the provider that actually reaches out over the network to communicate directly with those upstream cloud APIs. Because the core is kept so isolated, the provider ends up taking on some pretty heavy lifting. Its responsibilities include authenticating with the target infrastructure provider, initializing any required API libraries, and defining the specific resources that map to those unique cloud services. Going back to our analogy for a second, you only need to install the specific cartridges you're actually going to play. If you're only building in Azure, you just download the Azure provider. The brain stays perfectly lightweight, and the hands do all the specific labor. Which brings us to Section 4, connecting brain and hands. So how do they talk to each other? They communicate using RPC, or Remote Procedure Calls. In this client-server model, Terraform Core operates as the gRPC client, and the provider operates as the server. When Core determines that a server needs to be built based on its dependency graph, it simply fires off an RPC message to the provider. The provider then translates that internal Terraform message into the exact REST API call that the specific cloud platform understands. Let's move to Gina and see how this builds a real environment.
This hierarchical structure represents a dependency graph mapped out for an actual AWS deployment. You can easily see how Core logically orders the load balancer, the routing records, and then the instances. Once it's all mapped, it fires off those RPC commands, traversing right down this graph to provision everything in the precise required order. It's really quite beautiful to see it in action.
Section 5, DevSecOps and Best Practices. Because we're treating our infrastructure as software now, we absolutely must apply rigorous software security standards. You should always modularize your code, and rather than keeping those sensitive state files locally on your laptop, store them in remote locked backends like AWS S3 or Console to prevent team conflicts. Also, make sure you logically split your configuration files, like keeping your main.tf and variables.tf separate, just to keep your workflow super clean and manageable. So the crucial point is securing your supply chain through a practice called provider pinning. The Terraform registry uses protocol versions to decide which plugins are compatible. By enforcing and basically locking down the exact version of the provider cartridge your code uses, you're protecting your infrastructure from unexpected or potentially even malicious upstream breaking changes. It's a non-negotiable for enterprise security.
And finally, Section 6, Summary and Next Steps. Your immediate next step? Go explore the Terraform registry. Think of this place as the ultimate app store for your infrastructure. It's where you can safely discover and download the precise providers you need to connect your Terraform core to literally hundreds of different APIs and cloud platforms.
To summarize everything we've covered, Terraform thrives on a split architecture. The core acts as your brain and operating system. It builds the dependency graphs and manages the state of your world. The providers act as your hands and applications. They translate Terraform's wishes into concrete API calls for specific platforms. And of course, by utilizing DevSecOps practices like provider pinning, you ensure those multi-cloud operations stay incredibly secure. We've completely peeled back the layers today to see the beautiful logic running under the hood. With the brain and the hands now demystified, the power is entirely in your hands. So I'll leave you with this. Now that you know exactly how the internal engine works, what multi-cloud infrastructure are you going to automate first? Thank you so much for taking this time to learn with me today.